So I don't want to repeat what Paolo has already said, but I guess it's, the natural starting point is to ask, why do we need to know where jobs are located? And, just to echo what Paolo has said, cities function to connect, workers to jobs. And so understanding both where those jobs are and what are the important infrastructural links is critical to protecting the sort of well-being of cities. And we're aware that many urban transport projects now require information on job accessibility as part of project planning. So one of the natural uses of this data might be as an input to some of those accessibility estimates. So this project kind of falls within what I'm going to call a new wave of data science for development, right? So in the last 10 years or so, there's been a lot of efforts to deploy all sorts of different types of novel data sets to infer things about urban economies and different kind of economic indicators from non-standard data. So you're all going to be aware of very successful efforts to use things like nightlights data to predict poverty. Of course, we can use mobile phone data to predict where people live, where they work, how they move. There's been a wealth of recent studies that try to use open data on building heights to infer urban form in cities. There's been, also many efforts to use imagery, both satellite imagery, but also street imagery to detect all sorts of things, including the presence of firms in cities. Now, many of these different sources have limitations. Some of them are very difficult to access, expensive to access. They have limited and potentially biased coverage. And some of them only detect certain types of things. For example, Google Street Imagery can detect firms, but really only those firms that are visible from the street. So it's pretty good for commerce, but not for other types of things. And so what we wanted to do was really think about how can we detect the spatial density of jobs in cities. And that was sort of the project that we started out with that Paolo outlined. And that was really led by Samir Barzan, who did much of the analytical work at the University of Oxford, which is where I was based before I moved to UCL. Okay, so what was the main objective? The main objective was to be able to predict employment at very high spatial resolution and in any city worldwide. So we wanted to be able to essentially produce a map that could be, given to research teams and researchers for any city worldwide at a 500-meter grid resolution. Very importantly, and that was a sort of a stipulation from the beginning, the input data should be open data. So it should be data that anybody can access and download from the internet. And it shouldn't be something that needs to be collected in a bespoke manner for different countries and cities, or something that would need to be paid for. And so that was one of the prerequisites. Paolo collected data on 14 cities in Latin America and Sub-Saharan Africa in order to train our algorithm. So this is, and you'll see later that this data comes in, let's say, different shapes and sizes. But that was a sort of prerequisite for the project, that we needed some training data, and that needs to be very high resolution employment data. And the overarching objective is to show that this algorithm that we're going to develop can do out-of-sample prediction, which means it can predict the distribution or the density of employment for cities which were not in the training data set, which essentially is going to tell us that we can use this data to predict cities, any city worldwide. So that's something that most academic papers that try to do things like this, like predict poverty, predict the presence of firms, very rarely try to do out-of-sample prediction. It's a very hard thing to do because, of course, you have no information on the specific city in question in the data set. And so that's a challenge for any type of machine learning algorithm in this space. Okay, so what did we use? So our input data comes from a variety of sources, but predominantly OpenStreetMap and satellite data. So from OpenStreetMap, we have things like the density of major roads, of street intersections. We have public transport, bus stops, tram stops, things like that. We have the density of amenities. So we have sort of different categories, such as all amenities. We have shops, we have restaurants. And then we have the classic Google Earth Engine type inputs. We have the density of nightlights. We have urban land cover. We have lots of things like vegetation and things like that. So we have the standard inputs, but instead of having a subset of them, we sort of aggregated them all. And we have this quite large feature space that we feed into our algorithm. And of course, we have our training cities. So this was a collection of data sets that was painstakingly collected by Paolo and June from all sorts of different departments in the bank. And we ended up with 9 cities in sub-Saharan Africa and 5 in Latin America. Now, as you can see from the table, it's very heterogeneous data. It's from different years, different types of data. So we have travel surveys, firm census, population census, all sorts of different types. And very importantly, these data sets have different polygon sizes. So in some cities, for example, in Latin America, where there's on average better data quality, we have much more high resolution data, right? So we have quite small polygons. And so you can see some of the polygons are much smaller than a kilometer squared. Whereas in many of the sub-Saharan African cities, the polygons are much larger, reflecting a lower potential data quality, but a much more aggregate data quality. So this is just the reality of the situation when it comes to the training data sets. And these are things that are important to keep in mind as we move through the analysis, because they will explain some of the heterogeneity in our results. Okay, so what we do, one of the first steps is we transform all the data to a 500-meter grid. So in some cases, it's aggregating down, in other cases, it's aggregating up, but everything is transformed to a homogeneous 500-meter grid level. Okay, so a very natural first step is to just look at a simple correlation between our different input variables and our employment density in our 14 cities. And so we can see here that we obtain results that we would expect, right? So things like population and nightlights are very highly correlated with employment density. In terms of the OpenStreetMap features, we see things like the number of amenities and the number of street intersections is very highly correlated. We have low correlation with the intensity of vegetation and the terrain roughness. Again, that makes sense, right? Because you're less likely to have employment in places that have high vegetation and rough terrain. So overall, in terms of the full number of features, we end up with over 100 features and over 100,000 observations. So these observations are grid cells. So it's basically the sum of all grid cells across all of our 14 training cities. And of course, we have a different number of grid cells for different cities due to different sizes, different areas. Okay. So in the working paper, we present results for many different machine learning algorithms. Here, I'm going to focus just on 2. So we chose random forest to begin with because it's very good for noisy data, and we have noisy data. We have noisy data on both sides. We have noisy employment data for the reasons that we already discussed, and we also have, we would expect there to be quite some heterogeneity in how well the OpenStreetMap is mapped across different areas, right? So we have noise on the feature side as well. And so we know from the literature that random forest is very good for noisy data because of the way that it's designed and the way that it resamples subsets of the data over and over again, and eventually averages that it deals well with noise and isn't terribly sensitive to this type of noise. And we choose a very standard setup. We train on 80% of the observations. So this is 80% of the full set of 100,000 observations. So you can imagine 80% are randomly taken out. So in the training set, you have observations from all of the cities in there, right? And then we test on the remaining 20%. And so we see here with just a bog standard random forest algorithm with no modifications relative to what is typically applied, we get a very good R-squared, right? Over 0.8, which is, extremely respectable with respect to the literature. But we went a bit further. And Samira had the excellent idea that areas that would have high employment would not only expect to have high density of features in the grid cells themselves, but also would expect to be in an area in which the neighboring grid cells would also have high density. So for example, we'd have a large number of bus stops in a high employment grid cell, but you'd also expect a high number of bus stops to be in the neighboring grid cells. This is a very classic idea, of course, in spatial analysis. And so we term this as an adaptation of the algorithm spatial random forest. And what spatial random forest is the same algorithm, it's still a random forest, but we've added features. So every feature has itself and it has its neighboring version, which is effectively the density of the feature in the neighbors, right? So we end up, if we have X features in the first random forest model, we have 2X features in the second, the spatial random forest model. So effectively what we've done is we've added these neighboring features. And so what we see here is that the R-squared significantly increases, and we're up to 0.95, 0.96, right, for the model in which we train on all cities and we test on a subset of observations in all cities. And we'll come back to the situation where we test and train on different subsets later in the talk. Okay, so what this is telling us is, and why we refer to this as the missing cells, is that if we randomly take cells out of this grid cells from our full observation set, and we train on the remaining cells, we can predict those missing cells very, very well. That's not really what we want to do in the end, but that's a very good starting point. It points to a lot of structure in the data that we can predict well using these type of algorithms. Okay, so this is just a visualization of the actual versus predicted employment for Dakar and Senegal, and you can see visually it's very convincing. Okay, so one of the questions you might have, and we had, is, yeah.
What is the outcome variable, the number of employed in that cell according to the element data?
Yeah, it's the density. Yeah, it's like a normalized density. Yeah, a relative density. Okay, so one of the questions that we had was, okay, so it's very classic. Many of these algorithms that are out there use satellite information to try to predict, usually not jobs, but they try to predict things like poverty. And income from satellite data. And that's kind of a well-established field, and we were obviously very aware of that. And so we wondered what was the contribution of the satellite features to our prediction versus the contribution of the OpenStreetMap features, right? To what extent was the idea that OpenStreetMap amenities would be important predictors, did that hold up? And so what we did is we trained the spatial random forest twice, one with just features that were with the OpenStreetMap data, and one set which just had the satellite features. And we actually see comparable results. Now, of course, if you only use one set of features, you get a lower predictive power overall. So we're focusing again on the outlined figure there. And so we see about 0.76, 0.7, 0.79. So actually, they both do about the same, which was a little bit surprising to us. And then when you add them together, in the previous model we saw, you get this really high predictive power. But when they're just used separately, you still get a very high predictive power and about equal for both, which is very interesting. So this is telling us that both matter in the prediction. The next thing we did, of course, is a natural thing to do, is look at variable importance on an individual level, right? So which of the variables, effectively variable importance is just you leave out a variable individually and see how the prediction does. And so we can focus here on the first column, which is the column where we train on all cities. And we can see, of course, population, neighboring population. So the N in brackets denotes the neighboring version, the neighbor version of the variable. So we see population, night lights, we see N dBi as vegetation cover, we see amenities, and we see neighboring amenities, built up cover, etc. So we see things that make sense. And that correspond with what we saw earlier in the simple correlations in terms of the variables that have the most impact on the prediction. And we can also look to see whether these were similar for when we trained on just subsets, regional subsets, and we see some variation as you'd expect, but nevertheless, similar variables were important for all of the different sets. Okay, and then if we look at the most important variables, when we just constrain ourselves to the prediction that used only the OpenStreetMap data in it, we see that amenities, as we've seen, but also street intersections and the density of shops. So they would be the top kind of OpenStreetMap variables that would be driving the prediction in that case. Okay, so now that we have got a handle on how the kind of, let's say, global prediction works, our main objective is that we want to predict out of sample. So what does that mean in practice? What it means is that we want to train the algorithm on 13 cities and predict the 14th. So we want to basically predict a city for which no training data was input into the algorithm at all. It's completely unseen. And if we can do this well across the 14 cities, then we can extrapolate from that we can trust our prediction for any other city worldwide. And so that's our strategy, so to speak. Now, we're going to go backwards for a second. Okay, so we saw this table before, but we didn't zoom in on some of the information that was in the table. So we can see here, the rows are the test data. So we can test and train on different sets, right? So we can train on sub-Saharan cities and try to predict on Latin American cities, right? That's a much harder task, right? For the simple reason that if we're trying to train on sub-Saharan cities and predict Latin American cities, none of the information on the Latin American city is in the training set. So we're doing a sort of variation of this out of sample prediction already here, right? And we see that the R-squared drops significantly. Now that is what we would expect. And there are two possible explanations for that. So first is that there is a region-specific difference, right? That actually there's something structural that's different between sub-Saharan Africa and Latin American cities in the relationship between these features and employment. Or it means there's something city-specific. And so that leaving information out from that particular city in the training set means that your ability to predict the city is much lower. And so we can't necessarily 100% answer this question, but we in the subsequent analysis will get quite some way towards understanding exactly what's going on in the data and why. Okay, so as I said, our main objective was to do out of sample prediction. So what we've done is for each city, we have trained the algorithm on the other 13 cities, and we've tried to predict that particular city. And so you can see here a list of the R-squareds that we have obtained. Now, I want to emphasize that this is an extremely difficult task that's rarely attempted in the literature. And if you do find R-squareds in the literature, they're in the about 0.2 range, right? We haven't seen anything higher than that in the literature. So the R-squareds that you're seeing here, although they are significantly lower than the very high R-squareds we had for the full sample, they are much higher than what's in the literature, the very few examples in the literature. So here we see quite a range of values, right? We see everything from Harare in Zimbabwe being 0.2, all the way up to 0.7 in Buenos Aires. And we discussed earlier that there was quite a lot of heterogeneity in the input data, right? So we had some cities that had very small polygons and we had really detailed data, and other cities where we had very large polygons. And of course, all of this is happening at the grid level. So you can see that some data, is being really, we're trying to extract a lot really for cities that had originally very large training polygons, right? And so, very large input polygons. So one of the things that we suspected was that we can predict better for cities that originally had small polygons. And this little plot on the right is kind of confirming that, right? That we have a higher R-squared for cities in general who had originally better data quality, or that had smaller polygons to begin with. So what we decided to do, and it was actually a suggestion of one of the initial reviewers of the working paper, was to redo the R-squareds, but aggregating to the original polygon level. And so that's what we did next. And we find much higher R-squared. So the R-squared range is now from 0.3 to 0.81, but the 0.3 is really an outlier. And that's because Harare had very large polygons, and we suspect that that's really got to do with potentially bad data quality in Harare. But generally speaking, the R-squared is now, between 0.5 and 0.8, which is really very high for out of sample prediction. And it's probably due to two things. There's probably some city-specific variation in the relationship between the features and employment density, but there's also going to be noise on either side, right? So we're very happy with this kind of final result. And we think that we can conclude from this that we can do out of sample prediction very well. And when we evaluate the R-squareds at the polygon level, we no longer have this correlation with polygon size. Okay, so that's the overall analysis. And so the end result is that we can now produce these maps for any city worldwide, and they've already been used by various transport teams in planning. If you or your team is interested, you can talk to Paolo, who is the organizer of the map producing. But we do hope to eventually make a library of these maps public for use. And we're thinking currently about how to best use this data for academic and applied purposes. And we're going to show you now two follow-on projects that are in the preliminary stages, but they're, as Paolo mentioned, some of the things that we're thinking about that could be useful to do with this data that have been in our mind for a while. So I'm going to present the first one, and I'm going to hand over to Shu to present the second one. Okay, so the first question we asked ourselves, obviously we now have this unparalleled potential to look at the spatial distribution of jobs in any city worldwide. So it's very tempting to look and see whether we can first characterize polycentricity for global cities and look into whether the degree to which a city is polycentric, which could be defined many ways, is correlated in some way to the wealth of the city, the GDP of the city. Okay, so there is a very rich literature that looks at this question and sort of provides, let's say, theoretical support for this question. The empirical results that have tested this are varied, right? We have some studies that show some level of correlation between polycentricity and GDP or labor productivity, but then there are other studies that don't find any correlation at all. And of course, all of these studies use different methods to define polycentricity, but they also use very different data inputs. Some of them are using population data, some jobs, et cetera, et cetera. So one of the first questions we asked ourselves is, how should we measure polycentricity? Right, so there are different ways of thinking about polycentricity, and actually it's a little bit hard to keep track of some of these measures. I'm going to show you 4 measures. The first 2, the only thing I want you to remember is the first 2 are really about the evenness of the clusters. So a city is very polycentric if the clusters are roughly even sizes, right? And so many of the original papers we just saw in the literature review use this Green's measure. There's a little bit of a difference between Shannon and Green's. Shannon is really, it's an entropy-based measure. So it's basically telling us very straightforwardly something is very polycentric if the clusters are very even sizes. Green's is based on the standard deviation of the sizes of the clusters. So something that there's slight differences because sometimes things that might be have high Shannon entropy, so they're very polycentric from the Shannon point of view, may actually have low Green's because you can get sort of higher standard deviations from multimodal distributions. But anyway, that's somewhat of a technicality that we'll come back to. But there's a difference between these 2 measures, but they both essentially try to measure how evenly sized the clusters are. And so if you're very polycentric, you have very evenly sized clusters in general. Okay, and then the second 2 measures are more about the spatial spread. So these 2 they say nothing about the spatial spread of the clusters, right? The location of them. They're only comparing the sizes of the clusters, completely not related to the space. These 2 explicitly take space into account. So LASM is really a measure of how concentrated employment is. It doesn't deal with clusters specifically. It's just a measure of how concentrated employment is. So if your employment is not very concentrated, you have high polycentricity in LASM, under LASM. Batty entropy, and actually Michael Batty was the founder of the center that I work in, but it's called Batty entropy, and it's really how distributed are the clusters in space, right? So basically if you have high Batty entropy, high polycentricity from a Batty point of view, the clusters are very much covering the space. And of course, then this depends a bit on your definition of the spatial boundaries. And so, okay, so although we started out with an ambition of rolling out, this type of analysis for a global set of cities, of course, obtaining GDP data by city is actually very tricky. And so we're quite constrained in a sense, not by our ability to quantify polycentricity, but by our ability to obtain data on GDP. And if you look into the detail of many studies that look at city level GDP, they're actually downscaled data from national estimates, which is not really appropriate for our analysis. So we have managed so far to collect some data for GDP for cities in the OECD, so Bulgaria, Colombia, Mexico, and Turkey. We have some Chinese data and some Brazilian data. Each has a little bit their own issues, which we won't go into now, but we have done some preliminary analysis looking at the relationship between GDP and polycentricity under these 4 measures. I'm not going to go into too much detail here, but this is just looking at the correlation between these different metrics, right? So as we might expect, the Greens and Shannon, because they both look at cluster size, are very correlated. Batty and LASM, which both look at the distribution of the employment or clusters in space, are a bit correlated, but the others are less correlated, right? And so I think you can kind of group these things in your mind, right? So Greens and Shannon are very similar. Batty and LASM both look at distribution in space, but they're not very similar. They're quite distinct aspects of that, and they're sort of 2 categories in a sense. And we have some correlation between Greens and Shannon and Batty, but I think we can leave that aside for now in our minds. Okay, so the first question is, we can look at the relationship between GDP per capita and polycentricity. We actually put our data to quite a hard test here. We are controlling in all of our in all of our regressions for area, population, and elevation, which some of the other comparable studies actually don't do necessarily. So controlling for area, population, and elevation individually, Shannon, Batty, and Lassam are all significant for OECD, which was surprising to us, but they're all robustly significant. And if we put them in together in a multivariate setting, we find a stronger result for Shannon and Lassam. So this is sort of telling us that evenly sized clusters, cities with evenly sized clusters and employment that's really quite spread out over the urban area do tend to have higher levels of GDP per capita. Okay, so that's for the OECD cities. We have fewer of those, but they are defined as functional urban areas, which is identical to our predicted employment data. So they're very nicely aligned. With the Brazilian and Chinese ones, the spatial alignment is not as good. However, it's something that we're thinking more about at the moment. But we repeat the same analysis. And so in the Chinese cities, very different than in the OECD, we find that the Greens polycentricity is significant, which actually coincides with the literature that also finds Greens is significant, but none of the others are. And then Brazilian cities, absolutely nothing is significant. So there's a bit of a question mark here as to what's going on and to what extent is the OECD, results generalizable. Okay, so that's a little bit of an insight into what we've done in terms of looking at polycentricity so far. We find that Shannon and Lassam are very significant for the OECD cities. For the Chinese cities, it's Greens that's significant. Brazilian cities, nothing is significant. So that is, maybe asking some questions about some of the results reported in the literature as to whether they are, representative of larger sets of cities. Okay, so there's some next steps that would be, we need to fix some of the boundary issues. As I said, some of the GDP data reported for the Chinese cities and the Brazilian cities, the boundaries are different than our predicted employment data. For technical reasons, which I won't go into, it may not necessarily make sense to rerun the predicted employment for these larger boundaries, but we'll have to think about that. We can include more cities contingent on finding more GDP data. I think that's available for places like the US quite easily, but I think we're more interested in more middle income countries, so it's less available. Other studies do add other controls such as human capital and FDI. I think that's very doable, and potentially other urban form features, such as distance to the coast and things like that. Okay, so that's where we are in that project. And I'm going to quickly introduce the next project and then hand over to Shu to explain what we've done. Okay, so this is a project that grew out of an original question that Paolo sort of had, which was, how can we use some of this to identify critical road segments, right? Some of the ideas in here were evolved from some work that they've done with Yi, who was thinking already about some of the questions that we identify in terms of identifying important roads in cities and the computational issues associated. Okay, so I guess the overall motivation is that, as we know, climate impacts are increasing, and actually, there's increasing pressure on road systems and flooding, and that has a sort of knock-on economic impact in terms of people's access to jobs. So we're interested in identifying which roads are at risk from flooding. And so one of the sort of test cases that we've begun to look at is Kigali, Rwanda. And we want to know, how can we detect these critical road segments? Much previous work has really relied on, well, there's a couple of different schools of thought here, but one of the major schools of thought is to use network analysis and betweenness centrality to identify important roads. And effectively, a road with high betweenness centrality is one which is traveled on many times if you look at all the paths from A to B, from any A to any B in the network, right? So it's road segments that are transited very heavily when you compute shortest paths between any A and B. But this is very computationally intensive, and it also ignores completely where jobs and population is, right? It's just based on the topology of the network. And it's, as I was saying, very computationally expensive. So anything over 10,000 nodes in the network, it's virtually impossible to compute. And even just Kigali has twice that, right? Nearly 3 times that. So it isn't scalable for, large sets of international cities. Okay, so what was the objective? We want to develop an algorithm to identify these critical road segments. We want to use the predicted employment data and population data to weight this, in a sense, to capture important road segments for commutes. We want to make sure it's computationally cheap and scalable, using open data again. We need to validate this somehow, so using some kind of GPS mobility data to effectively convince us that the road segments we identify are, in fact, important congested road segments in general. And we eventually want to intersect this with flood data. Okay, I'm going to hand over to you.
So as Niamh was talking about weighting the betweenness centrality metric, one way we thought about doing this would be to add origin destination flows. So the way we go about doing that is using the gravity model, which kind of predicts or estimates spatial interaction in a city. Essentially, it looks at the flow between a point A and B based on the population and the employment in these points. So the flow between two densely populated areas with high employment would be higher than more sparsely populated areas. And of course, this is weighted by a distance metric. So essentially, longer people would travel less if the distance is longer between A and B. So the flow would be less between those 2 points. So we add this, we incorporate this idea into our betweenness centrality metric. What we do is we use population distribution to draw our origin, and we use the employment distribution that we get from the predicted employment data to draw our destination. And for and we keep iteratively doing this. We find the shortest path between the origin and the destination, and we add it to the street network, and we keep on recursively and iteratively doing this until the results reach an equilibrium. And by that we mean that the average travel time over the street network across 2 steps, the difference between that is 0.01. Okay, so once we have a fair bit of an idea of what we wanted to do, we looked back at the literature to see what work has been done in this area, and also how well these incorporating origin destination flows, how well it correlates with real world data. And what we find is, for the most part, origin destination flows are added using either mobile phone data or taxi demands. There's always this demand supply data that's added to modify the betweenness centrality metric. And usually it is validated using GPS data from taxis. And the correlation, as you can see, is fairly high. But one thing I would like to point out is that most of these papers focus on 1 or at the most 2 cities at a time. So it's very focused on that particular city. So the next thing we do is we look at the conventional betweenness centrality metric, and we compare it to our simulation results. And right off the bat, we can see that the 2 results are very different. For the conventional betweenness centrality metric, we see that these peripheral roads that almost avoid the centers, employment centers in the middle, or the city center, are seen to be weighted more and are more traveled on, whereas we, in our simulation, we pick up the more centrally located streets that go into the heart of the city, and which bring in maybe populations from the outskirts, of movement from the outskirts into the city center. But that's only the first step. And what we would like to understand is how does our approach compare to the real world traffic flow? So for this, we use an open source data, which is Uber movement data, which gives us the average number of pings from Uber taxis and scooters in a hexagon during typically between 10 a.m. and 6 p.m. And we have data for 5 cities, Madrid, Brussels, Lisbon, Rome, and DC. And what we do is we correlate the data we have from Uber with our simulated results to see how well our approach performs. So looking at the correlation here we look at three different approaches. One is where we draw origin and destination from the population distribution. So we are only looking at how people move within the city. Then we look at population employment data, where the origin is taken from the population data and the destination for the employment data. So we're focusing on commutes. And in a third step, we add amenities information as well. So these could be restaurants, hotels, and so on and so forth. And across the board, we see for all the cities that we have, we get correlation between 0.2 and 0.3 for the population employment and amenities data, which is already, it looks good. And I think what we would like to understand is what is going on, what are we comparing against in the Uber movement data, and what are we picking up in our simulation. So if you look at the map on the left, it's a visual representation of the real world data, Uber movement data that we have. And on the right is our predicted results. And we see that for the Uber movement data, there's a lot of congestion around, I would like to say, the White House, north of the White House. And then for our predicted data, we see the road segments that, once again, bring in movement from the outskirts into the city center are weighted higher and are way more prominent. But given that you've worked and lived in DC for a while, I would love to hear more about which one do you agree with more here. So what are the next steps? We have compared it to Uber data, but it's quite restricted in the sense that it's only collecting data between 10 a.m. and 6 p.m. So we might be missing the rush hour traffic data. So the first approach would be to look for another data source and validate our approach against that, for instance, Waze. The other thing that we would like to do is maybe add more variables. Are there other variables that we could possibly add to improve our predictive power? Maybe we could do it in a multivariate setting or a machine learning approach. And finally, we would like to see how we predict for unseen cities. So something that's not been done in the literature, where people focus on one city at a time, we would like to be able to do this globally at a global level, which I think would probably be interesting for the World Bank as well. And as the final step, coming back to our original question, if we once we identify these critical road segments, and we can overlay flood data with this information that we have, how can we identify the people and the roads that are most at risk? And eventually, how can this lead to infrastructure and housing planning in these cities? But the ultimate goal of this project is to create a global data set which identifies critical road segments, but also identifies areas where you could invest for infrastructure and for climate proofing, as Paolo pointed out earlier. So that's it. That's all for our presentation. Thank you very much.
Thank you. Are there any clarifying questions for the speakers before we begin? And I don't know if anybody is online.
So just before we go to Dimitri, there are quite a lot of questions online in the chat, and I've been kind of keeping track of some of them. So I'll try and fill those. But if I miss any after Dimitri discusses, then please do feel free to probably just unmute yourself and come in, or if that's too messy, to raise your hand, and I'll try and keep track.
Oh, would you ask them to come in, or we're going to just?
I was actually thinking that maybe we should go to Dimitri. I mean, if there are clarifying questions, that's great. But maybe if not, we can go with Dimitri and save the Q&A for later.
Up to you, honestly. All right, I'll just go, and then we'll see what happens. I also would like to get my remarks out of the way because, you know, I think there's many more smarter people than me in this room who will contribute much more profoundly. I'm coming to this from a kind of far less technical lens of these guys. What they do blows my mind. It's like magical and stuff. And I'm an urban specialist, so I've done quite a bit of analytical work, so I have experience with interacting with the different new sources of data, but much more on the kind of level where figuring out how to use it to bring to your clients and to make practical applications of it. So I really read the paper and listened to this with that lens, and this is where my comments come. So I mean, first of all, what I think I have. First point is, wow. This is amazing. This is amazing. Every time I discover something like this, I feel like, you know, a man who's been like opening his eyes because it's actually allows us to shine a light in the dark. It allows us to understand something that we couldn't understand before. I think, and that is relative in many ways. You know, I think I've experienced this in my work with a few types of data that then incorporate our work pretty routinely. Obviously, 9/10 lights, you know, the revolution 10 years ago now, pretty routinely used in new sorts of analytics when you look at urban economies. I have very cool experience of using Twitter data to see spatial attitudes of people to public spaces, which I think is also an amazing look at the urban landscape. I've worked on a project where we use mobile phone data to map organs destinations and at real scale over urban areas, and all of those just allow us to have a much more informed and deeper conversation with the world. And I think you're adding another critical and impressive layer to that toolbox, and that I just want to congratulate the team in advance. The next step with any using the zoning of this data is that state limitations. And that is always critical. You know, as from the data sets I've used, you know, like NTL, you learn that, like sometimes you learn that like, in high latitudes it's less precise, and that when the electricity goes off, you're going to have no data. Right? With Twitter, in some countries, the pickup and use is much slower, and sometimes it's flat. With mobile phone data, depending on which provider you buy the data from, the demographic of users may be different, and that skews your results as well. And those are the kind of things you need to be aware of. And that's kind of the next thing that kicks in my head. Well, now I can see this is amazing. Now, how do I make sense? And that's where I think really the real next step for me in this work applies, right? We have this amazing set of tools, an amazing data set that can shine a light on something we didn't know before. Now, how can we look at it and understand to what extent we can trust it? Or what kind of decision, what level of decisions is this data? And I think what you're doing is super interesting because you're really trying to identify specific applications, which is great. But I think it's kind of almost useful to try to move two directions. Identifying specific applications is amazing, and I think the road segments work is kind of a plug and play thing will be very useful. But also I think it's useful to think of kind of the rule book of at what scale, with what caveats this can be used. And I'll tell you how I'm thinking about it. You know, R-squared are great for understanding kind of the relationship between the cause and effect, right? The predictive power and kind of understanding whether we can make a rule in this relationship. It's less useful when you try to think, okay, can I make any conclusion about this specific pocket of the state and what I see on this map? And it would sort of be good to try to guide potential use of data through that. Like first, at what scale can you use? What scale of decision making is data being used? Is it for citywide sort of thinking? Is it to kind of at the level of city kind of broader districts, sort of 3 or 4 macro areas, understand where your points of urban of job concentration is? can you guide it to inform kind of your strategic spatial planning and like major trunk infrastructure in a very loose, non-precise way? Or can you go a level deeper to a neighborhood level and kind of understand prioritization of, for example, public space investment at a neighborhood level or trunk infrastructure investment at a level? Or can you even go to, in some cases, to a block level where this data can inform, for example, modeling bus routes or bus stops. So that's kind of the framework that I had in my head. Where is it? And how can we find a way almost like a playbook, a guidebook? In this set of circumstances, this is useful at this level. In this set of circumstances, this is useful at this level. So that's sort of an idea I had. And we were to deeper reflections about like whether we can move towards that. So it's having a playbook, or whether there are certain tests that can be applied to the data to sort of identify high or low worsenings within the same state or across cities at different scales. You know, that I think is something that would very much help people like me and other urban specialists to try to have these conversations with mayors and use that in our actual investment operations. So that was kind of my biggest point and my biggest kind of curiosity about how it is those things. I think the one sort of point almost on the side is that in the paper I read like almost slight dismissal of big data techniques, and so like spatial big data. This is a big word, okay? There's a big proposal, but you say that of course it's expensive, it has its issues. But the trick with big data is that it's as precise as you like. I mean, first of all, you know where it comes from. You know kind of you can usually know the profile of users, which goes both for mobile phone data or for apps data. And then it's down for loss. You know kind of what we're, and that gives you, again, it's a different lens. And I was thinking about how maybe there's a way of combining as a part of developing this table. Can we think of how we combine different data sources to kind of through that combination to build a picture? I understand. Anyway, thank you for this work. Thank you for the presentation. Really impressive stuff. And these are just some hopefully provoking.
So, Niven, do you want to react, Dimitri, and then we also open it up for the Q&A?
And there's a bunch of more technical questions.
Yeah, I saw. So, do my best to try and convey them.
Yeah, no, I mean, those are really good questions. We have been asked by a few people before, like in what city size, for example, can you apply this to, right? So, could you apply to a tiny town, for example? And so we have to use the training set to some extent as our guide, right? Because that's our only indication of what ground truth is, even though that in itself is quite messy, right? So I think, a rule of thumb and something that we discussed, although I don't know if we wrote down, was sort of a typical, you shouldn't try to use it on a smaller city, much smaller city than is in the training data set, right? Because we don't have much confidence there. I think when it comes to zoo, so of course the R-squareds we provide are at the polygon level, right? The higher R-squareds. So that's a quite good indication of, for what type of city we have confidence for, right? So some of the polygons are really quite small in Latin America. So I'd be pretty confident that in similar size Latin American cities, we could do very well, right? So say other Brazilian cities that are of a similar, quite relatively large size, I'd be pretty confident that we do well. So I think we have to use the attributes of the training set to guide what we have confidence in, because otherwise we can't know, if you know what I mean? There is no other external source to tell us what's the right scale, right? So I think, we've shown in the algorithm that we can predict really very well, say, for example, in Buenos Aires, at the grid level, the 500-meter level. So I would be reasonably confident around that level, right? I don't know, Paolo, what your reaction would be.
Yeah, no, I mean, I agree, and I mean, we should recognize there's some variation, right? We
Right,
do
yeah.
great in Buenos Aires, but not everywhere.
Yeah, yeah.
So there's that limitation, and unfortunately, what would be ideal is to have, 150 cities where we have training data to actually see if this is an outlier or if it's consistently. So that's kind of one response. But I think there's also the question of not only how well can we predict at a low level, but does that mean that we can also kind of influence decision at that low level, or should we only kind of be a bit,
A bit higher than that,
higher
yeah.
up, right? I don't know if you have
It's a very interesting question to ask. Let us take that away with us. If you were to say, write, a guideline note, right, to say what this could be used for, I think that's a non-trivial technical question to ask, right? But yeah, my instinct also would be to maybe not use it at the grid, but at maybe not too much bigger, right? I'd be fairly confident at a slightly bigger scale than that. But yeah, that's an intuition more than a quantified thing, yeah.
And just building maybe on that point, because I think it also plugs into one of the questions that is in the chat, where someone was asking whether we could look at areas which were maybe of lower socioeconomic status, potentially more informal, more slum-like, and quantify what the accessibility of these people are to jobs, and that. But if I'm answering for all of us, but I think that is something I would feel comfortable doing, and actually that is something that we were hoping to be able to do. We had this great plan with June also to kind of try and leverage some of the efforts which are there to kind of map slum areas in a vast range of cities. But we were in the end convinced not to do that for the moment. It was not that clear that the slum data was trustworthy at this stage. So I think that's not too.
Well, as in we heavily reviewed the algorithms available, and we were not convinced that what's on the market can do out of sample slum prediction. Yeah. Which is tricky.
No, I understand. It's universal and extremely unfair. There's a long respect.
So the other bit was about dismissal of big data. Yeah, I mean, I think that was not our intention to be dismissive. I think we were trying to make the point that data is, very tricky to get hold of, very costly and time consuming, and not available from many places. And if you want to do a global comparative study, for example, you want to compute polycentricity for every city, you couldn't do that with mobile phone data. So it was more, we were trying to be distinct in our offer and explain why a more open source alternative was needed, as opposed to being dismissive. I mean, we work with mobile phone data a lot. So there's a big attraction in combining the two. It's something we have discussed. There's so many things to do. But we're definitely interested in talking to people who would be interested in things in that direction. We have mobile phone data for Colombia, a lot of it. And I know that various groups in the bank have also countries. So we're definitely interested in doing that. But we hadn't really thought about like methodologically how they'd be combined, but of course they can be very complementary. Yeah, sure. But we'll tweak the wording. It wasn't our intention to. It was more like trying to explain why this was a solution to a different problem. Yeah.
Thank you.
Some of the features that you use to train the data are more immobile than others, like land use might change over certain. So how do you think of this as predicting today versus in 5 or 10 years?
Just jumping in, a couple of questions exactly along those
Yeah.
lines, right? In the chat, so hopefully this will answer also.
Yeah.
And I noticed too in the employment data, some of it is 20 years old, so I don't know from today. So I'm not sure exactly how you calibrate that. It's best to have for the impact.
Yeah, no, absolutely. Yeah. I mean, so on the feature side, we have discussed this, but again, not done it yet, which is some of the features do change in time. So in theory, if you were to leave aside the training aspect, if you were to believe the algorithm works reasonably well, you could then in some ways predict a temporal evolution of job densities, right? Because you could look at how these things change over time and feed them in and have an output. But then some of them don't really necessarily get updated or changed too much over time, right? So it's, as we showed, a subset, so both the amenity data and the satellite data both matter to some extent, and some of those change. I don't think the amenities are going to change massively. I don't think we have access to old amenities data, for example, right? So
Amenities, you do something that's really about OSM use.
no, what's in the OS, I don't think we have back data for that. I don't think you can get old.
Oh, well, you can.
Okay,
But
yeah.
I think the concern is always it's just the rollout of OSM to, crowdsourcing
Oh,
amount of our
yeah.
actions.
Yeah, exactly. So, I mean, we've thought about it, but not on a very deep level, I would say. We had I guess we had a feeling that something could be done in terms of exploiting some of the temporal variation in some of the data sets, like the satellite data sets are cleaner. But yeah, the OSM is.
I guess one question is, can you do a version where you restrict yourself to only using things that you think that you could? I mean, you could arguably
Yeah.
say an OSM road changes very fast. Land use from satellite data changes fast, but a few other things don't, right? So you can restrict yourself to only things.
Absolutely, because I mean, that's what we did in the middle part when we just did only OSM and only satellite features. So we, of course, yeah, we can, that is exactly what we discussed doing, was restricting the data set to certain variables that do change, and then producing a sort of, I guess, a map, evolving maps. As I said, we just haven't got around to doing that yet. But yeah, that would be really interesting. But we would want to validate that to some extent, right? And that we would need some temporal data to do that.
That is the blockbuster application that can get to prediction of job impacts.
It's actually a point I wanted to make. I remember discussing with Ayaan Majid a couple of years ago when we were actually thinking about this work or starting it. And I think that was exactly what she would have wanted us to be able to do, like actually picking up the impact of a project on the ground on job creation, which it sounds amazing. But what's happening? But yeah.
We published a note last year on operationalizing jobs in urban areas. And one of the key roadblocks for mainstreaming, like more economic, local economic development agenda in urban projects, is that we don't know how to manage gaps. We just don't have tools. We very restrict them.
I mean, some of the census data, like the Mexican and Brazilian census data, is very good and temporal. So we could maybe, like, one option would be to roll it out to a bigger set of Brazilian and Mexican cities and validate that using their temporal census data, which is also very fine grained. So that would provide a much more kind of like fine validation.
Yeah, that's my good.
Yeah.
It was a
You need to give us
symmetrical
some
question.
money for all of this, someone.
A symmetrical question about if there's a downturn in the city, would we kind of or in an area of the city, would we actually capture that? I think it's the same type of response, right? We'd actually need to try this,
Yeah,
test this algorithm
Yeah.
out against ground truth data to be able to answer that.
but it would be very, if we could get a hand on the Brazilian and Mexican census data, I think it would be for like much more cities and, yeah. Anyway, yeah, great idea, yes.
Question. So I was actually coming more from the disaster side of it. When you're talking from the OSM side, the same things actually happen, especially in developing countries where soon after an event, a lot of people come and they will actually develop their OSM data sets. This would be interesting to hear. We have actually looked at some of the cases like in the Philippines, check out some of the other ones where I know there are very big differences in the event where things that actually came up. So you can actually see what was there before the event. Like a reality, for example, and what actually happened afterwards. And what are those implications?
I think, yeah, again, mobile phone data might be even better for that kind of thing. But yeah, we can certainly look at the OSM. We haven't really looked at the old OSM data. We just have like slice.
Can we capture that? You done? Be like Google Earth where you can actually zoom back in.
Yeah, we have to check. Yeah, you think we can?
Yeah, it's one of those, about your coverage, one of those things.
Okay,
time,
Okay.
snapshots. of it.
snapshots in time, yeah. We haven't really looked into that, but yeah. Sure.
There's a question that has to do with the scale, not exactly the same scale, I think, as what Dimitri had in mind, which was, could we apply the model at the country level, so decreasing the resolution, but using kind of subnational employment data as additional input? This was thinking about country level, if I'm.
Yeah, I mean, I guess the question is to what extent then you're sort of, you obviously need high resolution training data, right? At the grid level. And then I guess the question is whether urban areas then, like, the thing you're trying to pick up in that case is urban, sorry, it's rural, right? What's outside of cities. And the question is whether does the density of OSM features and the density of nightlights correctly predict employment in those areas? That's the real question. I'm not sure. It's more obvious to do it in cities, right? But could you aggregate up then? Is that at the country?
My gut
Yeah.
feeling is that it would be a different set.
Yeah,
That
yeah,
it's probably worth
yeah,
exploring, but
yeah.
it wouldn't be about kind of aggregate. I mean, it wouldn't be this algorithm. Might be something that builds on this, but
Yeah. Yeah, I think the question of whether the same mechanisms are at play in rural areas, you could run this algorithm on some rural areas to see what the predictive power looks like. And to see if actually a lack of amenities is, you know what I mean, sufficiently, you know, because it might be different things, but yeah, yeah. And we could explore small town prediction, which is what we haven't. But again, I think maybe getting access to the Mexican and Brazilian census data for all of their cities could be like a way forward for like more fine-grained analysis.
Yeah, I think there's a lot of very high resolution data, but given, I think there are some particular challenges with Mexico and even Colombia and Ecuador that we recommend also, because I'm not sure how representative they are in terms of when they're looking to for the Asia Pacific kind of scenario. Because we have that in the school files in Mexico and the Colombian and some other the cities that actually are very, very different. And that, I don't know, that would actually manifest in terms of.
so if I can maybe on that, so the cities are super different. We all agree. I think that this is a different kind of difference we're talking about. Is it that they're different because things are in different places, etc., but the relationship between kind of urban form attributes and job density remains, or is it that that relationship itself is different, right? So you can have different things because of different reasons. That's it. And I think what we tested with the 14 cities we have, and I'm also answering another question here, is trying to test whether that kind of relationship that we were building kind of remained true across a larger number of cities. And we kind of at least made the leap of faith that, given the R squares we were getting, that yes. That said, we only tried this in Latin American cities and sub-Saharan African cities. We didn't actually manage to get our hands on cities in Asia, for example, on the jobs data. And I think that would be really interesting. I think there's someone that was asking about this in the chat, right? So right now we take that leap or make that leap of faith that we can actually predict based on what we know here. We can actually predict, for example, in a city in the Philippines, but we haven't actually validated that before. So.
People can hear me on that, but yeah, two quick questions. One is it possible to disaggregate types of jobs? Because it seems like currently in the load network analysis, you have to assume that all people from the city are equally likely to want to access all the jobs. But if you had some way of predicting different types of jobs, and the income groups or something within the city, you maybe have a refinement of which connections are likely, and that has put about Asian. But one and the other is, if I understand correctly, you didn't focus on this too much, but you seem to be able to identify the predictors of job location based on different features of the city. Doesn't that have a lot of implications as well? And that could be a step towards predicting the impacts of interventions in the city, whether it's just, new infrastructure or new amenities or something like that. Is that potential avenue of further research? But yeah, it is.
Thanks. On the first part, so yeah, no, we haven't really tried to predict different types of jobs. And part of the reason is that our training data set, our only ground truth here, is a real mixture of different things, right? Some of them are more formal jobs, right? Some of them are a mixture, some of them are travel surveys, some of them are, like censuses, some of them are firms, they're more formal jobs, and some have everything. I think the Mexican data has informal in there as well. So it is not a coherent set of, jobs in the training data set. And so we can't really disentangle. If we had a clean, if we had a training set where we had like clean data, where we had, this is different types of jobs, and we could try to predict those separately, that would be really nice. But I think that's not the data landscape that we're in at the moment. Even just finding, even some of the sources of some of those data sets is still unclear, despite a lot of work to try and identify them, right? There's just, there seems to be like a real dearth of this really detailed spatial data. So that means that we can't then disentangle further from our data different types of jobs. I don't know whether if we did get more detailed data that was a bit more consistent, we could probably then try and drill down a bit more on different income groups and things like that within cities, and try to get a better handle of kind of going back to this kind of manual idea of, where do we do better and worse at predicting, but that would require a different level of validation data, which we currently haven't had access to.
And there was this, piggybacking on what Chandler was asking, there's the same question about gender actually, in the different jobs according to gender. And I think it's the same type of answer. We don't have
No.
Possibly, if you aggregate up to the question on country level, then you could perhaps take into account these enterprise survey type data, more survey based, which are usually based on business registry. So you have an inventory of all the businesses in a country, maybe not very spatially specific, but you have sectors, jobs. But you wouldn't be able to get the spatial disaggregation.
Yeah, and I think the OSM and map data, the point is kind of the spatial bit, right? Like the input data is very spatial. So I don't know to what extent aggregating up. Well, I don't know. Yeah. I mean, we could. I mean, I feel like we did try out different grid size, and the natural thing to do would be to try different grid sizes to see how the prediction changes at different levels of aggregation. I feel like we did do that. Can't quite remember the outcome of it.
Yeah, if I remember, the 500-meter worked best,
Yeah.
but I mean, it wasn't like a drastic drop when she changed the resolution itself. But we only, I think, tested up to 2 square kilometers.
Yeah, we didn't go.
with
Yeah,
her.
yeah. The second bit about the features, I don't know if you, so I guess this idea that we could use this for impact evaluation of specific things is probably something that requires a bit more thought. It's a signal issue, right? Like obviously things are added to OpenStreetMap chaotically by random people at chaotic times, I feel like that's a slightly different project in a sense, but one that's really interesting is to see what you can identify from OpenStreetMap in terms of a signal of specific policies or specific activities, and how reliable that is. Sorry.
I think this is for very much maybe downstream of what we're trying to work program. I think another kind of nice feature to have eventually is like, what if the user brings their own data? Like in a specific project, someone might have a meter data on electricity use or something that they're not, you know, I understand this will never be global public good as part of this is your broader approach. Seems to be, but it would be good to have kind of move it to bring your own data.
Yeah. One thing that we are doing, which is another side project, which we didn't present here, but actually might have been nice to give a taster of, is the Nanami project, which is, so one question, so in my department, we have a very lively mastery program. We have to come up with all sorts of projects for them every year. And so one of the projects, a very talented Japanese girl took on last summer, was to try to see, so if you look at all the papers, right, that try to detect urban form from different, like from kind of, let's say, novel data, there are lots of different sources, right? There's building height, there's night lights, there's density of street intersections, like the literature is quite large. And generally people are trying to detect kind of economic clusters, broadly understood. And so we do have this project, which has actually had some really nice results, where we try to analyze how consistent are the clusters that are detected. So, you know, if you were to use building height data versus our algorithm, for example, like how overlapping would the clusters you detect be? Because obviously if you're going to use this data for identifying, let's say, clusters or urban shopping centers, for example, you want some level of confidence, right, that the data source you use is sort of, you know, what impact does that choice make? So that's some ongoing work, which is a bit related to some of these questions. It's a bit different as well, about, you know, how much does it matter what you use? And it turns out it really matters. I mean, that's not surprising, but it really does matter. You can't substitute, you know, building heights and find the same thing.
Maybe all of you want to briefly mention, so if anybody here on the call is interested in getting their hands on this city, this density data, what does it do? How much does it cost? How long does it take?
Yeah. So, yeah, I mean, please reach out to us. We've kind of been invest, and when I say us at this stage, I think it's easier to reach out to me and June, in the room. I think you've all got my email from the flyer. We've been investing in trying to make this algorithm, and Shu has done a lot of work on this too, kind of as scalable and quick to run as possible. It did come with a few challenges. So now we can really churn out cities quite quickly, basically definitely in less than a day, unless it's a hugely massive city. So that's basically in a sense, the cost of it is having someone that has to run this on one of the teams for that amount of time. So it's cheap. So please do reach out.
I think we've gone over time. So I don't know if there are any last burning questions or anything online.
I'm sure I missed a couple, but I did try my best to kind of relay. So
thank you, everyone. Great presentation. So we promised to share as well the materials with participants afterwards. Make sure we get that. Yeah, so I think it's following up and then just trying to also find these applications for projects. I mean, I was trying to think if I'm a data, I have this, how would I? What are all the ways to interpret it? What are the uses of making these complex models and things simple and easy to understand? But thank you very much. Thank you.
All right. That was good.
Sorry.